we often use Greek letters to denote parameters, and we'll use Roman letters to denote statistics. So for example, a population level mean, which is unknowable unless you do a census, which is really hard, is called mu, the Greek letter mu. And the sample mean we often denote with something like a y with a bar on the top, which is called y bar. Sometimes you'll see it as x bar. So we use x and y to talk about different variables, continuous, discrete, or categorical variables, and we use y bar, x bar to talk about sample means. Variance is a measure of how variable a value is in a population, and we'll go through these details in a lot more detail in a few minutes. But the population variance, so variance of the entire population, we use the Greek letter sigma, the lowercase sigma squared. And the sample variance, we use S squared. Okay, so I'm going to start talking about some of these statistics, and I'm going to use summation notation. I'm going to do a follow-up kind of chalk talk lecture on a whiteboard, if that is helpful to some of you, which I think it will be. So I'm going to use a lot of summation notation in the next few slides. And if this is confusing, I would watch this, take notes, try to get as much as you can from it, and then watch the follow-up lecture on summation notation, and then maybe rewatch this. So we use summation notation a lot in statistics, and it uses the capital letter sigma, which is another Greek letter, as a shorthand for add it all up, okay? So, and I'm going to use that in a bunch of slides. So basically, when we start talking about summary statistics, we're trying to summarize sample data, give you an idea for the central tendency of the data, like not the extremes on one end or the other, but what are kind of like the majority of the samples like, the central tendency. And we're also interested in the spread. Is there a lot of spread around a data point, or just a little bit of spread around the central, the mean or something? So the law of large numbers in statistics says that large samples will provide good estimates of the population level parameter. And so, for example, if we're interested in a probability, like a coin toss, we know in our minds, right, that tossing a coin is about 50% probability of getting head and 50% probability of getting a tail if it's a fair coin. So if we toss that coin, 1,000 times, most likely we'll end up with a number that's pretty close to 0.5 and 0.5 for those two probabilities. However, if you just toss your coin 3 times, are you going to get 50% heads? No. You couldn't possibly. With just 3 tosses, you can't get 50-50. You might get 25-75, right? Or, sorry, it'd be more like you tossed it 3 times, then you could have 1 head with 33% probability and 2 tails with 66% probability. So you'd be wrong. And the reason you're wrong is not that the coin isn't fair, but that you didn't toss it enough times to get a good estimate of the true probability. Okay, so here's your first big summation notation. The thing that's nice about this is that we're talking about the arithmetic mean, which you probably already understand to be the average. And so thinking about what you know about an average, you take all of the values, you add them all up, and then you divide by the number of observations. And so this is how you would write that in summation notation. You would say the sample mean y bar is equal to the sum of every value in the data set, all the y values in the data set. And we're going to use this y sub I to talk about each value individually. So we'll say every value in the data set y sub I plus the next one, the next one, the next one, and the next one, all the way out to n. So that's what this y equals the sum from I equals 1 to n, I equals 1 to n. Add up all the values of y and then divide by n, which is the sample size. So in this case, the y sub i's are the values in your data set, and n is the total number of observations in your data set. And so hopefully you have a sense for what this means and how you would write it in summation notation. So y bar is an unbiased estimator of mu, the population mean, when 1, observations are made randomly. 2, observations are independent of one another. And 3, the observations are drawn from a large population. That's that law of large numbers. Okay, other measures of central tendency are things like the median. The median is different from the mean in that it's a rank order value. So you would place all the numbers in your data set in order from smallest to largest, and then the median would be that middle value. Okay. The mode in a data set is the value that occurs most frequently. And so you would use a histogram to figure out the mode, and the mode would be the peak of the histogram. Okay, so those are the 3 measures of central tendency that you often hear about: the median, the mean, and the mode. Now we're going to quickly go through some measures of spread. The first one is called the sample variance, and all the rest of them are built off of this one measure. So it's really important that you understand it. So the sample variance, we call it S squared, and basically let's start with the summation part. So the sum of every value in your data set from I equals 1 to n of each value in your data set minus the mean value squared. Okay? And then you add those all up. That's what the summation part means. And then you divide by 1 over n minus 1. Okay? And then moving on, and we'll talk a little bit more about the sample variance. I guess I'll start by talking about it. So if you just took every value in your data set and subtracted it from the grand mean and then added up all those deviations, you would actually get 0, because you have half of your values are bigger than the mean and half of your values are smaller than the mean. And so that's the reason that this variance term is the deviation between the value and the mean squared. Okay, so, and that's why it's called S squared. So it's kind of easy to remember that way. Now, if you take the square root of the variance term, you get S, right? So S squared, you take the square root, you get S. And that's called the sample standard deviation. And this is used a lot. So just keep in mind that it's the square root of the variance term. And so what you see is all of this is the same as what's up here. And it's just all under a big square sign. And this measures the variability of the measurements around the mean in the same way that variance does. But it's not kind of, it's a more useful measure. The standard deviation is a more useful measure than the variance. So people don't often report the variance in their data sets, but they often report the standard deviation, or they report another value that's calculated from the standard deviation, which is called the standard error. The standard error of the mean is S sub y bar, or sometimes just SE for standard error. And it's basically just the sample standard deviation S divided by the square root of your sample size, n. Okay? And so what you'll see here is that whole squared value divided by the square root of n. And this is a measure of the variability of the estimate of the mean itself. And it's commonly reported on graphs. Another reason people like to report it on graphs is it tends to be shorter, smaller than the standard deviation, right? You're dividing it by the square root of n, so it makes your graphs look a little tidier. But it's important to know when you should be reporting the standard deviation and using it in the error bars, and when you should use the standard error. A few more measures of of spread are the quantiles and ranges. So just like the median is the middle number, if you put all your data points in order, you can measure the spread around the median using quantiles. And quantiles can be any percentage of the data. So the median is the 50th quantile. Often people report the 4 quarters or the 4 quartiles in the data, and that would be the 25% quartile, the 50% quartile, and the 75% quartile, with both of the endpoints. So it's really kind of five values, because it's the minimum value, the maximum value, and then the quartiles. And what you can do is you can put those into what's called a box and whisker graph, like at the bottom. You can see the median value, you can see the upper and lower quartiles, and then the points represent the highest and lowest data points as well. And these are really useful graphs. We'll try to make some in class. And the last measure of spread is called the coefficient of variation, or CV. And the thing that's nice about this is that it's a comparable value across all data sets and all populations. And the reason is that it's the standard deviation divided by the absolute value of the mean. And so here you can see, and hopefully it's not scary, but it's that same value here, which is just the standard deviation. And this time it's divided by the absolute value, so it can't be negative, of y bar, which is the sample mean. And it's often multiplied by 100. So jump will multiply it by 100 when you're calculating it in jump. Okay, so some graphing basics. Now that you know about the central tendency and spread around data points, you can start to make some really great graphs. So first of all, you need to know what kind of variables you're dealing with. So think really hard. Do you have a continuous variable for x or y? Do you have a categorical variable for x or y? Some kind of discrete or ordinal value. Ordinal means that it has some order to it, like small, medium, large would be an ordinal variable. And so when you're making a graph, you always put your independent variable on the x-axis. So it's some kind of a factor. JUMP calls it a factor. And you put your dependent variable or your response variable on y. So in this case, whatever variable is y is dependent on x. So like plant growth depends on how much sunshine the plant gets, right? You don't determine how much sunshine is there based on how much plant growth, unless, well, that's kind of a bad example. Shade can influence that. But in general, for most variables, you can determine which one is influencing the other, and whichever one's getting influenced is y. It goes on the vertical axis. Okay. Sometimes, and we'll talk about this in correlation, you can kind of flip-flop back and forth. It doesn't, one is not necessarily influencing the other. But for the most part, you're going to be able to figure out which is which. Okay, so here's an example. Here we have a bar graph. We have two streams. So stream is a categorical variable. It's on the x-axis. And if you have a categorical x, you're going to have some kind of a bar graph or a whisker plot. In this case, on y, we have a species diversity index. And that's a continuous measure. You can see it's going from 1.6 up to 1.75. In this case, the error bars, the bar height represents the mean, and the error bars in this case are standard error bars. Note there are axis labels. It tells you what your x and y variable are. Excel is really bad at making graphs without axis labels. And then there's some statistics on this graph. So there's a t-value. We'll learn about that in a few weeks. There's a p-value. We'll also learn about that later. But in this case, you can see we have a continuous y, categorical x, and those error bars are really overlapping. So it's based on the statistics, I know, and you will know eventually, that there's no difference between these two groups, or these two streams have the same diversity. Now contrast that with this graph. We still have a continuous y, categorical x, but now we have a significant difference between the two groups. So now you can see the bars are still showing the mean, and the error bars are still showing the standard error. Those error bars are much smaller now, and so and the statistics tell us that there's a statistically significant difference between these two streams in terms of species diversity. So here's a couple jokes. I'm a collector of statistics jokes, and so I apologize. You're just gonna have to put up with them. This one is a bunch of bars. It says, "I'm sorry, man, but we just can't trust you." And they're all looking at that one bar with the really big error bars. Here's another one. "Should we scare the opposition by announcing our mean height, or lull them by announcing our median height?" Maybe now you understand the joke. Yeah, they're really bad statistics jokes, so I warn you, they only get worse.